Okay, let's check on how to do local linear routine, and also apply to other simulations as well. So most likely, you will get something like this: a list of checkpoint, field file, moment file, energy file, parameter, tracer, efit, VSP, energy file, omega file. You can check what those means in Gene manual, but the routine that I've learned and I've used is such. I will have my cheat sheet here. So pretty much this. So that's the genecode directory, and then there's a inside genecode it has a built-in plot method. You can plot the energy file. This basically by default will give you electrostatic energy heat transport. And just keep in mind, if you do it in the remote machine, you can download xming, xmng. You can check this app, so that you can display a graph via SSH. And then tap L to have a log plot, so that you can see that C is a straight line instead of just wiggly. That means it's saturated. In other words, this simulation is done. It's well converged to one single mode. And as you can see, it's growing. And we're gonna talk about the diagnostic later on, but like a troubleshooting later on. But this is how to look at those things. And if you have an option -n space 9, that's an electromagnetic heat flux. Most of the time you for me, I want to look at electromagnetic because I'm actively searching for MTM. There you go. Species 0, 1, and 3, 0, 1, 0, 0, species 0, 1, and 2, based on the order of your parameter file setting. As you can see here, this is ion electron impurity. So as you can see, this electron have a higher level of a saturation ion impurity. Okay, so next we're looking at the growth rate. So what I wrote is then we can get into the script, the IFF script. Basically, in the IFF Institute for Fusion Studies, in UT, we're constructing a set of a Python script that does acting like a pre and post processing tool. You can get it in the GitHub. I will have put the link into the description. I will try to remember that. So I wrote a script. I think it's pretty handy. Pretty much convert the things that you want into SI unit. Convert from Gene unit to SI unit. So it's called SI max 00005. Basically, that's the simulation you want. So yeah, see, like there's a suffix, right? You have those suffix. I choose like 005 just for illustration purposes. And as you can see, all of them give the unit most of the time you're gonna use. in publications or whatever. And there's a frequency in like kilohertz. Anyway, sometimes it doesn't give you that. Like it gives you 0 or just straight up cannot find the file, because it's either unconverged or the gene doesn't think it's converged. So you can calculate the growth rate and frequency by hand, in a way. So do it manually. You need this line. It's from the script. You have a calc omega from field. So basically that calculates the frequency from the field file. And you get this. So you need to choose a section that you wanna do the average. I don't know the details. This is written by one of my colleagues. I think David wrote it. And you choose a section, say 20 to 30. 20, 30, enter, and then they calculate the growth rate and frequency. And you should accept. You can have other choices, either accept, manually enter, or not do anything. I want to accept. And you can do the SI unit again to look at, it's the same. And the next thing is to get a transport ratio. So it's a d-chi ratio. Pretty much it will calculate all the transport ratios. This acting as a really good tools to distinguish which instability it is. You can check to the fingerprint paper written by Mike Kotschenreuther. I will try to remember that. Try to remember to put that into my description. So pretty much you can see that for electron, it's electrostatic, and the heat transport due to the electron is stronger. That means it's it's dominant transported electrostatic electron heat transport. Sorry, and then as you can see, particle transport over heat transport is really small. That means the heat transport is dominating. Then we can see that the electron heat transport, electrostatic electron heat transport is dominating. Then it's likely to be like ETG in the pedestal. That's in my routine of interest. I don't know. Maybe for others, there's other possibilities. But yeah, it's a very handy tools. Another thing is a mode structure. The script is plot mode structure.py. It will give you the mode structure, basically field across the ballooning angles, and you can see the parity of such instabilities, and also more importantly, you can check if such simulation has enough resolution. If your simulation doesn't have enough resolution, you will see the inside, like here, like won't be a continuous round like smooth curve. It will be like really zigzaggy and not even a smooth curve. If it's not smooth curve, then you need to increase your resolution or imply other numerical method to eliminate the numerical issues. because the instabilities or the calculation could be a numerical instability or is not a physical. It won't be. It could be potentially not physical solution. And that's the phi, of course, is electrostatic, and here is electromagnetic. You can see the parity is right there. Is even parity. No, it's not even. Sorry, it's odd parity. It's even. It's even parity. Yes, even parity. Anyway, and I can maybe I can do the do my script. It's called a mode judge. It's a dangerous tool in a sense. It's fully automated. I wrote this. Script. Basically, you can go through the whole list. It's called the max mode judge. .py. What it output is pretty much it will calculate everything automatically and ended up giving you a CSV file like such. You can see the suffix is there, the list is there, and they will give you a suggestion of which mode it is and give you all the things that you potentially need for your analysis. And there's like the mode based on the e-parallel. Speaking of e-parallel, we should do e-parallel as well. Based on e-parallel, you can calculate which mode it is based on the transport ratio, which mode it is. You can see ETG. As I said, this is ETG, electron temperature gradient mode, based on all those transport ratios. So basically, you get everything we have done in this single file, which is pretty neat, I think. And I think I disabled the parity. I used to have an odd even parity to here you can calculate the parity if it's odd or even. Anyway, I think we're obligated to do the e-parallel. I think in the parity factor, here is the parity factor, and I think you can have the e-parallel somewhere. I think eigen, let me see. Yes, this one. It's really long, hard to remember, but I will put those in the description. 005. As you can see, here we have we plot the phi, kperb, and I assume they will give you e-parallel, which it give you kperb, which is good. KZ as well. I think I will try to remember how to calculate e-parallel, but yeah, those are the basic basic routines that I usually use, since Epar is not very important for me, but might be important for people who are trying to do KBM, kinetic ballooning mode. But I will try to remember that the script. Try to add the script in the description so that you can check them out. Anyway, thank you, and feel free to ask any question on the comment.